Now that we got that out of the way, let's go ahead and start running on chapter 7. Chapter 7 is about sampling distributions, okay? Sampling distribution. So we're going to do some samples from a population and we're going to talk about the distribution of those samples. Okay? So in other words, if you had a population and you took a sample, okay, so this would be your sample. Okay. So you have here what is called a statistic and a parameter. So if you go to page 442, it tells you what a statistic is and what a parameter is. So a parameter has to do with the population. Parameter has to do with the population. It's a characteristic of the population is a parameter. Okay, and then the statistic is with the sample. Okay. So in other words, if I have a mean here, if I have a mean in the population and the sample, I'm going to get a sample mean. Okay. If I had a proportion here, I will get a p hat, a sample proportion here. Okay. If I had a standard deviation here, I will get a standard deviation here. Okay. Okay. So you have to make sure that you get these things correct. Okay, if you go to page 442 in the bottom there, okay, well not in the bottom, but right above the example, it says that you have corresponding parameters and statistics. Parameters and statistics, parameters and statistics. Okay, if you start talking about the population, you're talking about the parameters, and you start using things that are over here, okay, you will lose points. Automatically, you will lose points when they're gradient, okay? Vice versa. So you have to get these things straight, okay? So in the population, you have mu, sigma, and p, whereas in the sample, you're gonna have x bar, s of x, and you're gonna have p hat, okay? So you have to get these things straight. You can't go back and forth with these, okay? All right. Okay, so let's move on to page 443, and it says the idea of a sampling distribution. Okay, we already talked about when we have the same population, and even if we have the same population, every sample is going to be different. Okay, every sample is going to be different. So every time I take a sample, I will get, let's say that I have a population here with a mu and sigma here. Every time I take a sample, I will get a x bar or a sample mean from that sample, okay? And then I can go ahead and I can take many, many samples and get many, many sample means. So the distribution of those sample means would be the sampling distribution, okay? So let's go to page 443, the bottom, there's a green box there, sampling variability. Refers to the fact that different random samples of the same size from the same population produce different values for a statistic, okay? So yeah, so you're gonna get many different X bars here, okay? Flip the page, the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Okay, just what we said, right? Again, if I take a sample from the population, if I take a sample, every time I take a sample, I'll get an X bar. Okay, and if I take many, many samples, I can now get many, many different X bars, and those are the distribution of those X bars would be the sampling distribution, okay? So let's go to the example on page 445 and see if we can actually read and see what this means, okay? So there's a problem there. Kayla, can you read the problem for us? The example, reaching for chips.
Yeah. So to determine how much homework time students will get in class, Mrs. Lynn has a student select an SRS of 20 chips from a large bag. The number of red chips in the SRS determines the number of minutes in class students get to work on homework. Mrs. Lynn claims that there are 200 chips in the bag and that 100 of them are red. When Jenna selected a random sample of 20 chips from the bag without looking, she got 7 red chips. Does this provide convincing evidence that less than half of the chips in the bag are red?
Okay, thank you. So you have 100 blue chips and 100 red chips in the population, right? And we took a sample of 20 and we found that we had 7 reds and we have 13 blue. Okay, that was our sample, okay? All right, so this is where we're at. Okay, we are told that we have 100 blues and 100 reds. Okay, we do not know that. Okay, the teacher told us that, but hey, you never know, right? So we take a sample of 20, and in that one sample, we got 7 reds and 13 blue. Okay, so here we go. A, what is the evidence that less than half of the chips in the bag are red? Okay, what would be the evidence on the side that says, oh, there are not the same number of blues and reds? Okay, the evidence is what? Well, I picked one and it was less, right? I picked one and I only got 7 red. So therefore, I am thinking there is a possibility that this is not correct. Okay, what would be the other possibility? What would be the other possibility? Caden, what's the other possibility?
The other one that we just picked less than equal numbers?
Yeah, so we got 13 and 7. So the one of the possibilities is that there are less reds than blue, right? So obviously the other possibility would be that yes, indeed, there are the equal number of blue and reds, but what caused us to get only 7 reds then? You just got unlucky, right? You just got unlucky would be the second explanation. There are 2 explanations here, right? Either there are actually less reds than blues, or there are the same number of reds and blues. I just got unlucky and picked 7 reds. Okay, so the question is, so if this was 11 and 9, would that be more convincing? That yes, indeed there are. It would be more convincing, right? Because you're only off by 1, right? But if you got like 19 and 1, now you really got a case here, right? How can there possibly be the same amount of blues and reds? Out of the 20 that I picked, I only got 1 red, right? Okay, so here we go. So this is what we're trying to figure out. We're trying to figure out, is this bad enough, or is this off kilter enough for us to confidently say that no, there are actually more blues than reds, and that's why I picked more blues than reds, right? So again, your argument towards that would be more convincing if you had the less amount of reds, right? The lesser amount of reds you got. In other words, let's say I only got 1 red and 19 blues, right? Then you're going to positively say, well, there's no way. There's absolutely no way that there are the same amount of blues and reds. Okay? Okay. So B, what does B say? Provide 2 explanations for the evidence described in part A. So we talked about the 2 parts, okay? We talked about that. C, there is 1 dot on the graph, okay? The graph is this is the dot plot of this is a sampling distribution, right? And this is P hat, because we're talking proportions here. Okay, we're talking proportions, so it's got to be a P. And it's P hat because it is the sampling proportion, right? It's the sampling proportion, okay? So in p hat, so what does the dot on 0.8 explain? So what that explains is, what does that mean? Is that what that 0.8 means is that on that sample, I had a proportion of 0.8% being red, okay? 0.8% were red, that means that you had 16 reds out of the 20, right? That would be 0.8, right? Because that's what that dot means, okay? D, would it be surprising to get a sample proportion of 0.35, which is what we got here, 0.35, or smaller in an SRS size of 20 when the actual P is 0.5. So justify your answer. So what does it look like? If you look at the sampling distribution, and I have 0.35, is that really far off? Is it, again, what is the words that we use in statistics? Is that statistically significant? Is this 7 or the 0.35 proportion statistically significant? What is your answer there? Mackenzie?
I would say no,
Why not?
because it's like within the range.
It's
an
not that
outlier.
far off, right?
Yeah.
How far off does it have to be statistically significant?
Isn't it 5%?
Correct, it is 5%, right? So it's definitely not within the 5%, correct? Which means that no, it is not statistically significant. In other words, it is not off kilter enough for us to positively say that there are not the same amount of blues and reds, right? So we can still believe there are the same amount of blues and reds, right? So there's no convincing evidence that there are less reds and more blue, okay? So E, based upon your previous answers, is there convincing evidence that less than half of the chips in the large bag are red? And the answer is no, because it is not that far off, okay? It is not statistically significant enough for us to say that there are not the same amount, okay? So if you understand this philosophy or this thought process, okay, this is the thought process that you will take with you for chapter 7, 8, and 9, okay? So you have to remember this thought process, okay? There are two explanations. Either what you assumed was correct and you just had an unlucky draw, or what you assumed correct is not correct, okay? So, and you're gonna do this by saying or looking at the sampling distribution and see if it is statistically significant enough to make that call, okay? All right, so moving on, let's go to the top of page 446. Top of page 446, it just kind of gives you a quick diagram of what the difference between a population distribution is, and the distribution of a sample data, and then the approximate sampling distribution, okay? So the first one there is the 50-50% of the red chips versus blue chips. The one in the middle is a distribution of the sampling data. So that would be this guy here, your 13 and 7. So you picked 13 blue and 7 red. Okay, that would be the sampling, the sample data, distribution of the sample data. And the one on the very right is the sampling distribution, is the, after you've done many, many different samples, how the X or the P hat, okay, how the dot plots plot out, okay? All right. Let's move to 447, describing sampling distribution, So if you look at, let's go back to that 446. If you look at that, what does the sampling distribution say? According to the sampling distribution, what should the population P probably of the proportion be? What is it most likely going to be? Eva?
0.5.
0.5. And why do you say 0.5?
It's the center of the graph.
It's the center of the graph. It's the mean, it's the median, right? It's everything there, right? Everything revolves around 0.5 there. It is symmetric across 0.5, or roughly symmetric anyway, right? So, I mean, it would only make sense if it was 0.5, right? Okay, so that is what you're looking at when you look at the sampling distribution. So let's move over. So you basically have a proportion here, and you're looking at the p hat, right? In other words, the p hat and the p are basically going to be the same, right? Or the mean of p hat, the mean of p hat is going to be the same as p, okay? All right. If you go to page 448, on the bottom, there is in the center portion, it says biased and unbiased estimators. Read the definition there. Definition says what? A statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution, is equal to the value of the parameter, right? Okay, so it's an unbiased estimator. In other words, there's no correction factor. There's no bias that you need to think about. It is exactly the same. Okay, so that's what we're talking. So what we call an unbiased estimator. Okay. Okay, let's flip the page. And all right, let's move on. So if we flip the page, go to top of page 451, it says variability. Variability is smaller is better. Why is smaller variability better? And the sampling distribution. Why is the smaller the better? The smaller is better is because you have a much smaller range that you know that whatever you're thinking about is going to be within. You have less variability, right? You want to be closer or more accurate as much as you can, right? So the variability being smaller is better, okay? And if you flip the page, it says choosing an estimator and choosing an estimator. So if it's unbiased, it's good, okay? Because there's no correction to be made. Okay, let's go to page 453. If you go to page 453, there are different types of estimators there, right? So if you go to A, they're trying to hit the target there. If you look at A, okay, estimator with a high bias and low variability. It's low variability because they are all the points are centered or they're all kind of bunched together, right? So that's what it means when it's low variability, but it is off the center, right? In other words, there's a high bias there. On B, it's an estimator with a low bias, which means that it's towards the center, but it's a high variability. It's kind of all over the place, okay? C would be the absolute worst because it is a high bias with a high variability. Then D would be the best. D would be the estimator with no bias and low variability, right? That's what you're looking for. Okay. So with that, we are done with 7.1. So we'll go ahead and take a stop here, and then we'll go start working on the homework.